Hey, I'm Mitchell. Welcome to another video in the RSP Education series. Choosing the right communication protocol can make or break an industrial automation system. You got Profinet, Ethernet IP, Modbus TCP, OPC UA, EtherCAT, whole lot of them. Each one of them offers different speeds, topologies, and strengths. In this video, we're going to break down the key differences and show you exactly where each protocol fits best. From real-time motion control to large-scale SCADA networks. If you're designing or upgrading or troubleshooting automation systems, this is the foundational knowledge you need to get it right. If you like this kind of content and want more educational videos, please like and subscribe. Also, this video is for educational purposes only. Consult a professional for your application. RSP Supply is not liable for any misuse of this information. With that said, let's get right into it. So when discussing industrial communication protocols like Profinet, Ethernet IP, Modbus TCP, OPC UA, DMP3, EtherCAT, Profibus, HART, the factors of communication speed and network topology and industry preferences, these are critical in selecting which protocol is best suited for any given application. We're going to give you a detailed breakdown that's framed in the context of industrial automation. So discussing communication speed, it's a key factor since it determines how quickly data is transmitted and processed within the network. These are often going to be categorized as real-time or deterministic with very minimal latency, or non-real-time, best effort with higher latency. So for real-time communication within automation, we're going to use a lot of Profinet since it's designed for real-time industrial automation with options for isochronous real-time, IRT, for high-speed applications like motion control and synchronized operations like robotic arms and conveyance. EtherCAT is also for high speed, extremely fast, deterministic, makes it ideal for high-speed robotics, precision motion control, and real-time automation systems. Ethernet IP also supports real-time communication using CIP sync and CIP motion. This makes it suitable for time-critical automation tasks. CIP sync syncs device clocks on an Ethernet IP network. It makes sure that everything happens at the exact same time. It's used for syncing input-output, time-stamping events, and triggering actions together. CIP motion. It uses CIP sync to control motion devices like servo drives. It also lets multiple motors move together in perfect coordination. Going to be used for high-precision motion like packaging machines, robots, or CNC systems. Profibus. It offers real-time capabilities, though it's a bit slower compared to Ethernet-based protocols like Profinet or EtherCAT. Now let's discuss some of the non-real-time communication protocols for automation. That's where we get into Modbus TCP. It's simpler, widely used, but not designed for real-time or deterministic applications. It's suitable for slower, less time-critical automation systems like HVAC or basic monitoring. Think of like water or oil. OPC UA. It focuses on interoperability and data exchange rather than real-time performance, although it can be adapted for real-time automation systems with additional configurations. DNP3, also non-deterministic. It's primarily used in utility automation like SCADA systems, where real-time communication is less critical than reliability and data integrity being a higher priority. HART, it's a slower speed protocol that's used for process instrumentation. In automation, it's not suitable for real-time control, but it is excellent for diagnostics and configuration. Now let's get into network topology. What do we mean by topology? Network topology refers to the arrangement of devices in an automation network and how they communicate. Some common topologies include master-slave and peer-to-peer. Each of these have pros and cons and have implications for system design and flexibility. Within a master-slave topology, the way that it works, one device is going to act as a master. That's usually a PLC, a distributed control system, or SCADA system. All the other devices are slaves. Devices like field devices, sensors, actuators, VFDs, etc. The master is going to initiate all communication. Slaves can only respond when asked. Slaves do not talk to each other directly. Some example protocols you're going to see in the master-slave topology: Modbus RTU, Profibus DP, DeviceNet. What are their use cases in industrial automation? So say you have a PLC, or the master, and it's gathering information from several temperature sensors, the slaves. And it's doing this for readings within a chemical processing plant. Some pros of this topology: it's simple and deterministic. It's easy to control data flow. Great for centralized control systems. efficient for pulling devices at regular intervals. Some of its cons: it's got a single point of failure, so if the master goes down, the system halts. Scalability limitations, so performance can drop with too many slaves. Slaves also cannot proactively send data unless prompted by the master. So the master-slave topology in automation, right? We discussed it's found with Modbus TCP. Modbus TCP is going to use a master-slave architecture where the master initiates all communication. This kind of simplicity makes it easy to implement, but less flexible for complex automation systems. Profibus, it's typically using a master-slave structure with the master controlling data exchange. It's widely used in process automation and manufacturing. Heart, it's going to operate in a master-slave mode. When the master or a controller pulls or gathers information from field devices for data. It's commonly used in process automation for instrumentation. DNP3. This often uses a master-slave model in SCADA systems with a central master station that controls multiple remote units in utility automation. So we covered the key protocols like Profinet, Ethernet IP, EtherCAT, Modbus TCP, OPC UA, DNP3, and HART. And we broke down how speed, topology, and use case are going to impact your selection. From real-time motion control to large-scale SCADA, choosing the right protocol is all about matching the tool to the task. Up next, we're going to show you how to design a mixed protocol network that keeps everything connected and running smoothly. For hundreds of thousands of other industrial automation products, please go to our website, rspsupply.com, the internet's top source for industrial hardware.